Okay, so let us take up these questions. So first, let's look at problem 4.7. A process is given for measurement of heat capacities. This experiment is named after the people who first used it, Clement and Desmos. So this is known as Clement and Desmos experiment for measurement of specific heat capacities of real gases. Okay, so this is something which you can actually design in your laboratory also. So once you are here, you want to do a design project to make up this equipment, you can set it up. Okay, so I will just first list out various steps in the process. So from 1 to 2, you have an adiabatic reversible expansion. So of course, this will be the hardest part to simulate in laboratory conditions, how to ensure reversibility. But so of course, no real process would be reversible, but you can ensure that you are very close to reversibility if you can make sure the process is slow enough. Okay. Then from 2 to 3, it is given to be isochoric compression. And then 1 and 3 are connected via an isothermal process. Okay, so that's the overall process which is happening. Now step 1, 2 I will focus on. So under certain assumptions, for example, constant heat capacity, adiabatic reversible, I have already mentioned. So using those assumptions and constant heat capacity, even though for real gases we know heat capacity is a function of temperature. If the temperature change is not large, you can assume Cp to be constant. I will also discuss how to account for temperature dependence of heat capacity. Okay, so this is step 1, 2. Here I have two unknowns presently, T2 and Cp. So I want to get rid of one of them. So I will leave it to you, but I can tell you that given on the basis of given information, which is given measurements, T2 can be obtained. So P2, P3, T3 are given. From these three, you can obtain T2. So that I'm leaving to you as an exercise. So now you can clearly see that only unknown is Cp. So you can solve it. Okay, so here I had assumed Cp to be a constant, and that is how we obtained this equation. Alternatively, if for the same step I want to account for temperature dependence of heat capacity, I will need to also rederive the adiabatic process relationship. Okay, so we start at the first law. Assuming pressure is low enough, I can still assume ideal gas conditions are valid. For P, you can use the ideal gas equation of state, or vice versa. To eliminate V, you can use the ideal gas equation of state, either way. Okay, and CV, you have an equation. For Cp, and from Cp you can get Cv. Okay, so that is how you can obtain the initial formula for temperature dependence. So now, because it is not an explicit equation in T, you will need to use an iterative scheme. So you do that, and you can, options are either you use the Newton-Raphson method, which requires a good initial guess. Option 2 would be to use Picard iterations. So that is, so have you in your numerical methods course come across Picard iteration scheme? Yes, no?
So
You're not audible. What did you say? Anyway, I assume the answer is no. So in Picard iterations, we set up any equation. Let's say the initial equation is given as gx equal to 0, and you want to solve for x, and the equation is implicit in x. I set it up in this form, and this is general. I can set up any given equation gx equal to 0 in this new form, x equal to fx. Okay, so that forms the starting point for Picard iterations. So now you will make an initial guess, and the good thing about Picard iterations is that it has better convergence properties. I will show you how. So I will make an initial guess. On the right hand side, I will calculate fx at x naught, and you can see as an output, I will get the new value of x. And then typically in Picard iteration scheme, we do mixing. So the new estimate, so let's call that as x1 prime for now. So the new estimate for x is obtained by mixing the old and the new. Okay. So clearly, if you take alpha equal to 0, you are using the full new estimate. Typically, that is not done. So you will take alpha actually very close to 1. So if alpha is equal to 1, then nothing happens, right? If alpha is equal to 1, you will just keep shifting between x0 and x1 prime. So you will not take alpha equal to 1. But if you take alpha arbitrarily close to 1, you will get a slow progress. But you will not face convergence issues. So it is clear this use of this method requires some initial cycles to understand what will be an appropriate alpha value of alpha. And many times one can mix Picard iterations with Newton-Raphson. So initially you can do a few Picard iteration steps so that your initial bad guess is refined to a better estimate. And after that, you can move to Newton-Raphson to speed up convergence. So you can use a combination of Picard iterations and Newton-Raphsons also. Okay. Any query?
no, sir.
Let us look at 4.15, which is a throttling process. So I'm directly going to write down the simplified energy balance. We've already discussed the assumptions which go into obtaining this balance. All right. Let us also now draw it on the PV diagram. If you recall earlier, I believe in chapter 2 textbook problem, we had one problem where nitrogen was near ideal gas conditions, and under throttling conditions or during a throttling process, very small change in temperature was observed. Okay, so now the conditions are different. It's not nitrogen gas. Okay, we are looking at benzene, but the main point here is the conditions are quite different, and that has a huge implication on the level of cooling you're obtaining in a throttling process. Okay, so the initial condition is given to be saturated liquid at some pressure P1, and after throttling, the end state is given as ending at P2. Once I tell you the pressure and I tell you it's a throttling process, we will do this practice later on once we have more handle on doing enthalpy calculations. Okay, but you will be actually able to tell the state. Okay, if I tell you state point 1, if I tell you pressure of state point 2, that would be sufficient for you to tell me that what is the end state after throttling. Okay, so here the end state is liquid vapor coexistence. So let's say this line kind of shows me the process. So this set of given conditions is typical of refrigeration cycle. So this throttle equipment is seen in a refrigeration cycle. And the conditions which are given here, that means I'm starting near a saturated liquid, ending in the coexistence region, are very typical of refrigeration cycle. Okay, so my expectation is I must get large degree of cooling. Only then it will be of use for a refrigeration cycle. So let us see if indeed that is happening or not. So at initial condition, the temperature is the saturation temperature. It is given it is saturated liquid. So for benzene at given P1, I can calculate the saturation temperature. For example, using Antoine equation, if it is not given, in the given case, it is actually given. Okay. So for the, if you go through the problem statement, the saturation temperature is already given to you. Otherwise, I could have calculated it from some relationships like Antoine equation. T2 sat is also given to you. So you can see I'm getting a very large degree of cooling. Okay. Close to 100 degrees. Whereas in chapter 2, I believe it was just a few degrees, 1 or 2 degrees. All right. So here in the problem, what they're asking us is, we want to pinpoint the position of state 2. And for that, I need to know how much vapor is present in state 2. We give that a special name. We call that as quality. So the fraction of vapor in a stream is known as quality of the stream. Why we are calling it quality would be clear once we discuss turbine operation. Okay. But for now, let's just say that we are giving this variable a name, quality. And typically the symbol used is X to denote quality. All right. So let us now see the details of calculation, how I can calculate X starting at delta H equal to 0. So that is my starting point. State 1 is given to be saturated liquid at some conditions. P1, T1. Okay. And of course, T1 is T1 side. Okay. I take my reference at some P0, T0. Let's say my P0 I define as P2, which is 1.2 bar. So now enthalpy in state 1. I need to account for temperature change. And I need to account for pressure change. So this first part accounts for delta T. Pressure change is very small, less than 10 bars. Liquid properties are weak functions of pressure. So here it's a very good approximation to say pressure change will not affect enthalpy. However, if you want to calculate it, again in chapter 6, we would learn how to calculate liquid, gas with pressure as well as temperature. But for now, anything less than 20-30 bar, even less than 50 bar change, you can safely ignore effects of pressure on the liquid state properties. Okay, so that's what I'm doing here. For state 2, the liquid enthalpy can be written as Cp into T2 set minus T naught. I'm assuming the liquid specific heat capacity to be constant. Plus, I have to account for phase change also. So presently, what I have obtained by writing Cp into T2 set minus T naught is a saturated. So remember because I've defined my reference state, this calculation is being done according to that reference state. So what I'm saying is I'm going from a liquid at P naught T naught to a liquid at P naught and T2 set. So when I go from P naught T naught to P naught T2 set, the enthalpy changes Cp into T2 set minus T naught. Okay. So this gives me saturated liquid enthalpy. P naught is same as P2. So at P naught and T2 set. Now I realize that the end state is not a saturated liquid, rather it is coexisting liquid and vapor. So I assume some fraction of that liquid has converted to vapor. Let's say the amount is X, which is our unknown. And the corresponding enthalpy change would be the enthalpy of vaporization at this temperature. So that is enthalpy of state 2. Delta H equal to 0 means H1 must be equal to H2. So you equate H1 to H2. The only unknown in this equation is X. So you can solve it. It's a simple linear equation. The only, let's say, difficulty you might see is in S, because Cp is already given in the problem statement. So how to obtain the enthalpy of vaporization at T2 sat? So you can first obtain the enthalpy of vaporization at the normal boiling point. So there is a relationship given in the book to obtain enthalpy of vaporization at the normal boiling point. Then there is one more equation which allows you to go from T1 to T2. So if I know the enthalpy at one temperature, enthalpy of vaporization, I can estimate the enthalpy of vaporization at another temperature. So that is the second relationship. So using these two, you can obtain the enthalpy of vaporization at the target temperature. Any query? All right. So that is how you can essentially solve for 4.15.
Sir,
Yes.
which part accounted for the changes in moles? Like there will be mole change also now, and we haven't multiplied with N1 and 2 sort of things.
Why there will be a change in moles?
Because it's a pure saturated liquid, and then there's pressure change, so some of will vaporize or condense depending on them.
So see, my path is here. My reference is P naught T naught. Okay. And from there, for state 1, I went to P1 T1, which is a saturated liquid at P1 T1. Okay. Starting from reference at P naught T naught. In the next case, again starting at the same reference, because if I don't keep the same reference, then I cannot cancel out the reference point. Okay. So here, if you can clearly see, once you do H1 equal to H2, T naught will cancel out. So it's important to keep the same reference point. Otherwise, the reference doesn't cancel out. So I'm first converting it to a liquid, saturated liquid at P2 T2. So 1 mole at the reference has been converted to 1 mole of saturated liquid. Okay. So up to this point, I had 1 mole of reference which has been converted to 1 mole of saturated liquid. Let's call this as delta H, first part. Okay. Now in the second part, I'm converting a fraction of this liquid to vapor. So I have saturated liquid 1 minus x moles plus saturated vapor x moles. And that I'm accounting for by the next addition, which I've done. Let's call it that at delta H2. And by that second change, I am left with 1 minus x moles of liquid and x moles of vapor. Okay, so I have accounted for that a part of liquid is going to vapor and material balance is being accounted for here. Is that clear from the path now?
Yes, sir.
Okay, so I first obtained the enthalpy. So I can follow any arbitrary path. So my path was, I went from a reference liquid state to a saturated liquid state, and then some moles of that saturated liquid were converted to a saturated vapor. Okay, so that is how I obtained the enthalpy in state T. 4.19 actually is the next problem. Which is asking you to calculate the flame temperature. So the very short definition of flame temperature is the maximum attainable temperature. So we assume the process to be adiabatic. Therefore, all the heat that is released by the combustion is absorbed within the material. Okay. So therefore, I will get the maximum possible temperature. The second requirement to get maximum temperature, which is not always in our hand, I will come to that point, is complete conversion of reactant. So in that sense, the second aspect especially, it is you can set up an adiabatic reactor, no problem in that. But the second aspect is not always in your hand. So, but for now, we'll solve the problem assuming complete conversion of reactants, and then I will address the issue when it does not happen. And the answer is it never. Okay, so it's always in a practical issue. So if you are practically carrying out this experiment in the lab, you will always need to account for the second aspect, which is complete conversion is not possible. Okay. However, in the problem statement, they are saying that complete conversion of reactant has happened. All right. So let us first try to attempt this part. So I'm carrying out this at constant pressure, the standard state pressure. Okay, so that piston cylinder might be one option for me to carry out this combustion reaction. And I insulate this to ensure adiabatic. So I apply the first law. So first I need to know what is the governing equation for the process. Adiabatic, so Q is 0. If the combustion reaction proceeds slowly enough, so if I ensure that combustion reaction doesn't proceed quickly, I can write down the work as reversible work. Or actually in this case, if you are maintaining constant pressure, then external pressure is P naught. So even if the process is irreversible, you can actually write down the work term as minus P delta V. Okay. So because here the external pressure is being kept constant. So even if the process is not reversible, external pressure is constant, you can write down the work as minus P naught delta V. All right. Which essentially means if you combine these two terms, you are essentially claiming no enthalpy change in the reaction, which kind of makes sense. Okay, so whatever reaction happened, everything got absorbed within the system. So no enthalpy change. That's when you will get the maximum conversion. Okay. So if I draw this process, I had reactants at 298 Kelvin. I have products at some unknown temperature. Now, and I know in this, along this conversion, enthalpy change is 0. Perfect. Okay. However, if you go back to the lectures, what we have learned is calculating enthalpy change of the reaction at 298 Kelvin, not at any arbitrary temperature. Okay. So I am free to devise my own path because I'm talking about enthalpy changes. So the convenient path here would be to first carry out the reaction at 298 Kelvin. So I convert my reactants into products at 298 Kelvin and then account for the sensible heat changes for the products, taking them from 298 to the target temperature. Okay. So I'm breaking down my entire process into 2 steps. Okay. The reaction is given to me. For combustion reaction, I will write down water in gaseous state because that is the expected end state. Okay. And you will see for the combustion reaction, even though we have said for H2O, the standard state would be liquid, but for combustion reaction, the reason we are using gaseous state is because the end state of water in combustion reaction would be vapor, and the heats of formation are given to us for both liquid end state as well as gaseous end state. So as long as we are careful, no problems. So now let us look at the feed conditions. I take my bases as 1 mole of fuel. I'm using air in the combustion reaction. And if I assume that I have taken stoichiometric amount of oxygen, that means I should take sufficient air so that I have 3 moles of oxygen. If I have excess oxygen, I will need to account for that in my calculation. So nitrogen would be, assuming air is 79:21 mole ratio, (11.286 moles. Okay. So in step 1, you had a reactant stream at 298 Kelvin. So it always helps to draw this table. The reason this table helps is you will need to do specific heat capacity calculation for sensible heat changes. So I start with 3 species. I end with my products at unknown temperature T. So this is the composition of the product stream. Delta H for this entire process at standard condition. First part is reaction. You can multiply it by alpha, which is the conversion amount. Okay, so that is how you can model the real process also. So if there is full conversion, to 1. However, in combustion, in this calculation, if you are going to do it in laboratory, typically the end temperatures are very high. And at those very high end temperatures, you have to account for reaction equilibria. That means the reversible reaction would be finite. You cannot completely ignore it. Okay. So typically you will need to account for reaction equilibria, and alpha will be less than 1. Okay. But for now, let us first do calculation with alpha equal to 1. The second part, I for now just write in a simple fashion. The Cp naught within brackets, triangular brackets, is mean heat capacity. So I'm not taking it to be constant, but we have defined this mean heat capacities or average heat capacity in the lecture class. You can calculate it from ABCD values given for each species. So in simple terms, this is the calculation you need to do. Okay. And delta H naught, that means the reaction heat, can be obtained from heats of formation. So this we have already seen in the lecture class, how to calculate the heat of reaction, standard heat of reaction. The input would be heats of formation of individual components. The table is given in the book. From there, you can calculate delta H naught to add 298. Okay. Now let us look at this last term, which is the mean heat capacity, how to calculate this one. Okay. So definition is given in the class. I will just show you how to do it here. So all you have to do is multiply by the number of moles of the species, the temperature dependence of the specific heat capacity of the given species, and integrate from 298 up to the target temperature. So this, and of course you will need to add the other two terms because here you have three species. So this summation will give you, so this is in a way the definition of mean heat capacity. Okay. So that is how I will calculate the mean heat capacity. All right. So from here it's clear that this mean heat capacity is in fact a function of temperature. That is function of T. So keep that in mind. When I put this delta H naught equal to 0, I obtain again an implicit equation in temperature. And the reason the equation is implicit in temperature is because mean heat capacity is a function of temperature. So again, you will need to do the solution in iterative terms. So you will first take an initial guess for temperature. In this case, it is very easy. You can assume Cp to be a constant, add and give the value corresponding to 298 Kelvin. That is the initial temperature. So assuming that constant Cp, you can get an initial estimate of temperature. Carry out the iteration after that. Okay, so I will give you an kind of a little bit of hint. Okay, but again, you have to complete yourself. So the initial guess, so this is in a way already set up in Picard terms. On the left hand side, I have T. On the right hand side, I have a function of T. Okay, so this is set up like a Picard iteration. So for initial guess, take the specific heat capacity of all the species to be at 298 Kelvin, the initial condition. Okay. And from there, you can get your initial estimate of temperature. From there, you can get the new estimate of temperature. Once you have your new estimate of temperature, calculate the mean heat capacity from the formula given at the top, because now you know T, you can carry out the integration. So we'll get a new estimate of the Cp naught calculated at T1 prime. You can do mixing if you want, etc. And you can repeat the iteration. So the steps are exactly the same as discussed earlier for Picard iterations. The specifics I have mentioned now. So now someone had asked about how to account for temperature dependence of Cp in this problem. So is that question answered? please speak up so that I know whether your question has been addressed or not. Okay. So all of these problems, I will highly advise that now at least try to solve yourself. Otherwise, it will not be clear. Okay. So 4.39, I will leave to you. It is in terms of calculations, very similar to 4.19. The details briefly I will mention. It's an adiabatic process. And also the conditions are maintained in such a fashion that the process occurs isothermally also. And the way it has been achieved is two reactions have been carried out. One of them is endothermic, other is exothermic, and they have been balanced such that the respective heats cancel out exactly. So respective heat changes cancel out from the two reactions, and therefore you end up with no change in temperature during the reaction. In fact, they're asking you what should be the ratio of the components in the feed so that the two reactions exactly balance each other out. Okay, so that's what you have to actually calculate. So the unknown here is feed composition. So at what feed composition the two reactions will cancel each other out. That means the heat generated by the two reactions will cancel each other out. That's what you have to estimate, the working equation which you will get. So in one reaction, CO2 moles determine what is happening. So let's call this as reaction A. In the second reaction, oxygen moles determine what is happening. We have already discussed in the lecture as well as in 4.19 how to account for temperature changes during a reaction. This is a very important calculation and it will require some practice for you to be able to do for various. So the difference between 4.19 and 4.39 is in 4.19 the reactants were at 298 Kelvin, products were at some higher temperature. In 4.39 both the reactants as well as the products are at a higher temperature. So the details of the calculation will change somewhat, but the procedure will not change. So make yourself familiar with that procedure so that you can complete these calculations. For this case, I will give you the answer also. If you practice this problem, you can be pretty sure that a lot of problems of this chapter you can attempt. So this ratio of the two sets of moles, CO2 versus O2, can be written in terms of, because you are using air, not pure O2. So after some simplification, you can write that as point in terms of X, where X is the moles of air. So you have a flue gas. I'm assuming I have 1 mole of flue gas and X moles of air. That is the initial composition. Okay. So for each mole of flue gas, I have X moles of air, and you have to estimate how many moles of air you need per mole of flue gas for this reaction to exactly balance each other. And the answer comes out to be 19.155. Okay. So I've expressed the ratio in terms of X rather than CO2 is to O2. X is moles of air divided by moles of the flue gas. Okay. So that is a change I have made because that is what is given in the problem statement. Flue gas and air are given as two components. Any query on this? So the last problem, I believe that is problem number 5. based on a bomb calorimeter. And this we are now using to calculate the heat of reaction for an unknown reaction. Okay, so there's any kind of calorimeter, their aim is to determine either heat capacity or heats of reaction. Okay, so this I am using to determine heat of reaction for some unknown reaction, and we have already calibrated this using a known reaction. So if you go through the problem statement, two sets of reactions are given. Reaction 1 is the known reaction for which standard heat of reaction is available to us. We use that known reaction to determine something known as calorimeter constant. So a known reaction is used to get this calorimeter constant. I will show the maths in a little bit. And then the knowledge of the calorimeter constant is used to get the heat of reaction for the unknown case. So that is the procedure which has been followed here. So again, first I will draw a schematic. So there is a cell within this bomb calorimeter where you put your sample as well as oxygen for burning. You have a large volume occupied by water or some other fluid. This is to ensure small delta T, right? So if you compare this against the flame temperature calculation, 4.19, there also you're doing the same thing. You are burning a fuel. There, if you complete the calculation, you will see the temperature change is very large. If the temperature change is very large, you will not be able to calculate the heat of reaction at 298 Kelvin. Okay, so here our aim is to keep delta T as small as possible, as close to 298 Kelvin as possible, so that I can directly get the heat of reaction at 298 Kelvin without making any other assumptions. Okay, so I put a large body of water outside my sample cell so that whatever heat is being generated by the combustion reaction leads to a very small change in temperature. So that is our aim. All right. So the process is constant
Uh,
volume. Yes.
can you repeat why small delta T?
A small delta T to ensure that I stay 98 Kelvin so that I directly get the required quantity, which is heat of reaction at 298 Kelvin. Okay. So once I do the maths, it will be clear how it helps. Okay. But the aim is so that I don't have to do any other approximations. I can directly obtain heat of reaction at 298 Kelvin. So it's a constant volume process. So for a constant volume process, heat of reaction can be written as internal, or let's forget about heat of reaction, but heat exchange can be written in terms of internal energy change. Okay. QV is the amount of heat generated from the process, and that is the heat which is being absorbed by the surroundings. The surroundings in this case is the calorimeter. Okay. So Cc is the heat capacity of the calorimeter material. Again, because delta T is small, I can safely take Cc to be constant, the specific heat capacity to be constant. That is the second advantage of keeping delta T small, because this equipment I am using for making accurate measurements. If I want accurate measurements, my assumptions should be as accurate, as valid as possible. Okay, so assumption of constant Cp is very good if delta T is small. And the reason I'm putting minus sign is because Q must be the heat perspective. Heat from the system perspective would be minus the heat from the surroundings perspective. The surroundings here is calorimeter, therefore the negative sign is coming. Okay, so this second term here is the Q of surroundings. Sorry, minus Q of surroundings. Okay, so Q for the system would be minus Q of surroundings. That is why the minus sign. And for delta U, there are two contributions: reaction plus sensible heat change. So again, assume the reaction has happened at 298 Kelvin and there is a small change in temperature. So I have to account for that sensible heat change also. Okay. So let us first write down this left hand side. Let us say I had NS moles of sample. So that will be known to me how much sample I started with. The internal energy change for the combustion reaction is delta U naught. Plus I also need to account for internal energy change corresponding to sensible heat changes. So that is my left hand side. Again, we have learned how to account for this quantity. So the end products would be combustion products, which are CO2 and H2O. In this case, H2O I'm taking liquid state because I'm ending very close to 298 Kelvin. So the end state in this case would be liquid H2O. Okay. And whatever excess oxygen I'm using. So here it is very important to use excess oxygen because we are assuming complete conversion of reactant, complete burning we are assuming. Okay. So complete combustion assumption would be appropriate if I have excess oxygen. Okay. So these are my products. The temperature of my products has increased. Accordingly, sensible heat calculation I have to account for. Okay. Right hand side I have already written. So the heat of reaction I take out on the left hand side now after some readjustment. And the other side I get the calorimeter change as well as the changes that are happening for the products. So these are your products. So this without any approximation, again, you can write in terms of mean heat capacity. Collect the two terms. So this I am defining as a new pseudo calorimeter constant, Cc prime. Okay. So Cc was the calorimeter constant corresponding to water. Cc prime involves contribution from gases also. For gases, specific heat capacities are stronger function of temperature. However, because you are keeping delta T small, so Cc prime is not actually a constant. But if delta T is small, Cc prime can be approximated to be a constant. Okay, so that is the second place where keeping delta T small, I am making sure my assumptions are as accurate as possible. Okay. So from the first reaction, so from the known reaction, I will estimate the calorimeter constant. And then I will go to the next part, which is for unknown reaction from the same equation. Of course, the values will change because the species is changing. For the unknown reaction, I can get delta U naught or something which is of more interest because typically all the tables do not give you internal energy change, but rather they give you enthalpy change. Okay, so how can I relate the two? So what is the relationship between the enthalpy change versus the internal energy change for a reaction? Okay, so that is the last part which is left here. So use the definition of delta H naught. So for calculation of the delta PV part, I am noticing there are some liquid species. For liquid species, delta V will be very small. Similarly, for solid species, because initially your sample could be a solid also. So for liquid and solid species, I ignore the contribution of this delta PV term. Therefore, I only need to consider the contribution from the gaseous species. Again, I'm making an approximation, but it is what I call as an engineering approximation. It is a very good approximation. I don't have to worry about the consequences of this approximation. Okay. Delta PV only for the gaseous species. Okay. Because the pressure is low, I can model the gaseous species by ideal. So I can use the ideal gas equation of state, find out the change in the moles, the gas moles during the reaction. So delta Ng is the change in the gas moles, and calculate the relationship between delta H naught and delta U naught. So just show you one example of the given reaction, how to calculate delta Ng, and then we will be ending this tutorial session. So this is your starting species. I will write in the condensed form. For stoichiometric amount of oxygen, because rest would be just cancel out. So I'm just considering the stoichiometric amount of oxygen. Whatever excess oxygen you have, that will cancel out. It will not contribute to delta Ng. So this is the reaction. From here, you can find out that you have gotten 7 moles of gaseous product in the, or gaseous species in the product. 15 by 2, which is 7.5 in the reactant side. So delta Ng in this case would be minus 0.5. If the reaction changes, this will also change. Okay, so you have to be careful about that. So this is the procedure you will follow to get the unknown delta H naught. And the final answer for the unknown reaction, the delta H naught comes out to be around minus 6300 kilojoules per mole. That was the target to calculate this quantity. Okay, for the unknown reaction. Okay, so again, you can check your calculations by arriving at this answer. Any questions, queries?
So in this particular question, the delta N gas RT would be ignorable, right? I mean, small.
You have to check. So it might be, you are right, but I have not actually looked at that. So I have actually included this in my calculation, but you can try that. Okay, you can see how much it is contributing. If you ignore it, what is the error you are making in delta H naught for the unknown reaction? Okay.
Okay. Yeah.
I agree with you, Aditya, that most likely it is going to be small, but I did consider it. So you have to do the make the effort. Try to see if you ignore this term, how much error you are making.
No, actually, I got it by 10 kilojoule of difference, so I thought maybe it is the delta N gas well apart.
Say it again. What did you get?
69, 6297 sort of.
Okay. Yeah. So yeah. So maybe, and you did not include delta NGRT part.
Yeah.
Okay. Yeah. So I think then we have our answer that it is going to be uh, negligible in this case. Okay. But if delta NG is large, then maybe it can have a significant error also. But that depends on the particulars of the reaction. If I had a heavier species, maybe this would have a more important contribution.
Uh, Also, in the first question, what did we have to find? I mean, ABC or CP value for that particular case? You talked about iteration, so what was that part?
No, so see, ABC might be available to us. Or okay, so you're right that if ABC is not available, then I can get multiple solutions to that problem. I will need to think about that. So yeah, because I had only one iterative scheme. With that one iterative scheme, it might become difficult to calculate the individual coefficients. Yeah. Let's say that iterative scheme would be handy only if ABC were available and you want to find out the temperature and temperature in the adiabatic process. So let us go at the top. Yep. Right. So if I assume A, B, C, D are unknown from one equation, I will get multiple solutions for A, B, C, D by using these iterations. Okay. So rather, if I wanted to for the adiabatic reversible case, yeah, and find the unknown temperature given A, B, C, D, I can account for temperature dependence of specific heat capacity. So this procedure I will use if A, B, C, D are given to me and I want to find out the unknown temperature. But you are right that for the CP calculation, I cannot use this equation. I mean, even though it looks like I can, but in practice, I will get multiple solutions of ABCD if I want to do iterations with only one equation. Okay. Yeah. So if I want to estimate temperature and account for temperature dependence of heat capacity in an adiabatic reversible process, I can use the right route I have shown here, the iterative scheme. Okay.
So, how do we actually find ABCD? Just if there are no other doubts, maybe you can just.
I need more data. So I need just single temperature estimate of CP will not help. So here the problem I have is I have only a single temperature point estimate and I have four unknowns. So if I, let's say, carry out much extensive calorimetry experiments so that I have CP value as a function of temperature at many more points, right? So the minimum you can imagine, if I have four unknowns, I need 4 points, right? If I want to do curve fitting, I have four unknowns. The minimum requirement would be 4 points, but that will give me a very poor estimate. So I need many more points to do curve fitting. So this is going to be a simple curve fitting calculation. Larger the number of points, better will be your confidence in the estimated parameters. Okay. So I need estimate of heat capacity at a much larger value or much larger range as well as many more data points. It's above 2. So those who have classes, they can leave. Those who have questions can still ask those questions. The session is anyways getting recorded. So any other questions, queries? Stop recording and close.